So good afternoon, and welcome to the final part of our scientific program of today. It has become a tradition that after the parallel sessions we are still gathering here as a whole conference, because after this presentation, which we are looking very much forward to, I will give you a very few instructions for tonight's reception, which I think a lot of people believe is a party, including me. Before that, we have the privilege that we will have another keynote, and it gives me great pleasure, and also I have to say that I'm personally happy to introduce to you my friend Wiiliam Chueh from Stanford University. Will is an associate professor in the Department of Materials Science and Engineering and Energy Science and Engineering, a senior fellow of the Precourt Institute for Energy at Stanford University, and a faculty scientist at the Stanford Linear Acceleration Center, SLAC, which is a national lab in the US. You have even more positions than I have, Will. He leads a group of more than 30 researchers with the following missions: understanding reactions and transport involving ions and electrons, and at the same time decarbonize various energy transformation pathways. He directs the SLAC Stanford Battery Center and the Stanford Storage X initiative. I don't know whether you have heard about the Storage X initiative, but during the COVID time, it was basically one of the very first, let's say, institutions starting an online seminar every Friday morning in California, Friday late afternoon in Central Europe. You can then see various speakers, and I think during the time of COVID, this was really kind of an icebreaker and bringing us closer to the virtual way of presentations of scientific achievements and more. Will has an enormous number of awards. I don't want to mention them all simply because we want to save some time. But I just want to mention the David H. Shirley Award, just recently, last year, the Friedrich Wilhelm Bessel Research Award 2022, the Volkswagen BASF Science Award, Electrochemistry, which is actually for younger scientists. And then, because I like the name so much, it's the Caltech Demetriades Zafka Kokkalis Prize in Energy. That was from 2012. And today we will hear something and learn something about building better batteries faster. Welcome, Will Chueh. Good luck, my friend.
All right, Martin, thank you very much for the warm introduction and for the invitation to come. Before I start, I just want to say I came here to also learn about the battery innovation ecosystem in Germany and in Europe, and I am extremely impressed at the tight-knit connection between academia, national laboratories, and also industry. This is something I will bring back to my colleagues. I think there's much for us to duplicate in the United States. So what I want to do today is to give you the American version of how we are trying to build better batteries faster. And I will give you the answer as well. We think one of the key ingredients is to bridge across all scales. And as I'm from the United States, we have to be a bit cheesy from time to time. We're going to try to connect things at the atomic scale all the way to the deployment scale for the entire planet. And I'll try to highlight a bit of that in my talk today. So to get started, this is a diagram I like to show as a material scientist and a chemist of how we can start at the fastest time scale on the order of a single ionic hop and at the nanometer scale, and work our way up from chemistry to the nanoscale, to the microscale, electroscale, device scale, and finally the system scale. And here we are combining synthesis manufacturing tools, characterization, modeling, and analytics. Something that has caught our attention in the past 2 years is the need to add a fourth scale, which is the economic scale. And I think this concept is no foreign to the community here, that we really need to think about lithium-ion batteries and beyond at the deployment scale where there is a strong incumbent of today's lithium-ion batteries. And in order to make impact globally, we have to have successful commercialization. And connecting these four big scales is really the challenge. And what I want to do today is to weave together a common thread. And that thread is the following. Across these scales, we can integrate large and multi-fidelity data sets, combine that with data-driven engineering and physics-based models, and use advanced data analytics to have understandings and actions across materials, cells, and even economic scales. I'd like to begin the talk with just an overview of the take-home messages. I'm going to start from the top and work my way down. So starting at the very right, the economic scale. Here, we believe that quantitative technical economic modeling should be a key factor in deciding early-stage R&D roadmaps. So for a scientist like myself working at the materials level, we also need to be informed on how these innovations would then translate 10, 20, 30 years down the road into a commercial product, even though we're very far from that. And this is in partnership with my colleague, Professor Sally Benson. Then working our way down at the cell level, and we have heard this topic quite a few times today already at the conference, understanding and predicting lifetime of batteries, especially under realistic conditions for electric vehicles and ESS application, is very much needed to accelerate the development cycle, and it's going to require understanding at the chemistry level as well. And then, because I'm a material scientist, I want to put one example at the materials level at an emergent opportunity and a call to those who are working in the mechanics field to look at material mechanics as a key frontier for developing higher reliability batteries. So at the cell level, I have the pleasure of working with my colleague, Simona Honori, and then at the mechanics scale, I'm working with my colleague, Wendy Gu. So let me get started with the economic scale. So here, let me describe how we've been thinking about it, say 10, 15 years ago, which is coming from the left to the right. We are developing fundamental technological breakthroughs in materials and devices, and we are betting on these breakthroughs to have impact at scale. But often we don't think about what that impact could look like quantitatively. But today, because this is a thriving and well-established market, there is also a strong incumbent, as I mentioned, we now need to work from right to left to think about what it would take to deploy at the terawatt-hour scale, even though we're working on the early stage R&D. And this is driven by the time criticality, because we will need to compete with present-day technology, which is also progressing very rapidly. And through a program that we have launched just this past year called STEER, we are trying to combine these elements together. We're trying to combine the technology, which includes both the devices and the processing, with the supply side, all the way from the mines, with the demand side, looking at the market. And even beyond just batteries, we're also looking at integrating the entire energy system. Battery is simply a small part of the entire energy system. We can think about the interaction, for example, with the electricity grid, the competition for electricity, for hydrogen electrolysis, and so forth. And by incorporating these four elements together, we have a holistic view of how the technology will impact the world at the economics level. And we're doing this very quantitatively. Let me walk you through the major pillars. We're looking at the learning rates of the technology, so how the technology will progress with deployment. We're looking at the fundamental material cost floor and the material supply chain. We're looking at the device engineering. We're looking at the market growth with time, and we're looking at the energy system as a whole. So to give you more examples specifically, we're modeling the learning rates of each individual component inside the battery for both present day and future technologies. We're also looking at the historical and future pricing of all key minerals. We're looking at today and tomorrow's cell design to inform the material's intensity. And then finally, looking at how the demand would grow as a function of different market scenarios. So when you put these four elements together, we can then predict what the future market and pricing would be of battery technologies. And I'm now going to take you on a deeper dive and address a topic that's been discussed several times today, is how can we make sodium-ion battery economically competitive? All right, so let's do a deep dive here. So we start by modeling all of the individual components in the battery, tracking today's costs as well as the learning rates. And what we have done is taken LFP graphite as the main comparison and the benchmark. And here we make a gross assumption that we can duplicate all the learning rates from lithium-ion battery and translate it to sodium-ion. So this is an aggressive assumption, what I would call the best case. So essentially, we're assuming full drop in learning rates. And here in this plot, you can see we have modeled the historical component pricing and also predicted the future component pricing. And we have predicted that by 2030, we will reach $56 per kilowatt hour for LFP graphite, which is coincidentally announced by CATL as today's pricing. So it seems like we're even already a little bit off today, but this pricing is indeed possible for LFP graphite. Then we duplicated this analysis for today's ready-to-scale sodium-ion battery technology based on the sodium nickel manganese oxide cathode with hard carbon anode, and translated the component learning rates. And then we're able to predict the pricing of sodium-ion batteries into the future. Because there are many unknowns, we are simulating scenarios across three axes. The first axis is technology. Because the technology is not staying put, there will be enhancements to decrease the material intensity. There will be enhancements to improve the performance. There will also be different market scenarios. For example, how much of ESS, 2- and 3-wheelers, and even EVs would adopt sodium-ion technology. Finally, there are also supply chain scenarios, specifically the supply chain of lithium, nickel, and carbon materials. All of these various scenarios would dictate how the pricing would evolve for a future technology and how that is benchmarked against the incumbent of lithium-ion batteries. This is already now public, so I direct you to the paper for details, but I want to highlight the crucial findings. So we looked at the baseline technology case of taking today's energy density of about 160 watt-hour per kilogram today, and we assume we can get it to about 200 by 2028. This is considered an aggressive plan, and we're talking about manufacturing ready, not just in the lab. Taking this scenario, we then predict the pricing of sodium-ion batteries for the next 20 years. So you can see in green, we have LFP graphite, and in red, we have the sodium-ion technology based on this technology roadmap. And what we are interested is when there will be a pricing advantage for sodium-ion or cost parity. And that's shown on the right. So you can see, based on our projection, price advantage will not be achieved until late 2040s for this aggressive technology scenarios. And this is not the only scenario we explored. We explored a total of 5,000 scenarios looking at different technology roadmaps. And one of the most important takeaway is that we, as scientists and engineers working on early and mid-stage R&D, need to really think about how our advancements in the lab might translate 20 years down the road and terawatt hours deployed. So let me give you the summary of the technology roadmap. So we consider 10 different technology roadmaps, looking at various enhancements to the cathode, to the anode, enhancement to the energy density, and enhancement to the material intensity across the battery. On the right, I'm showing a plot of all the scenario we have looked at. The legend shows you the price advantage year. So white means it never happens, blue and dark blue means it happens right now. And on the y-axis, I'm plotting the various supply chain scenarios. So in the middle, we have the baseline case. Above, we have condition which is unfavorable for lithium ion, which means expensive lithium and other raw materials. On the bottom, we have advantage unfavorable for sodium ion. And then on the x-axis, we have energy density, essentially describing the material intensity. What is really surprising is what I have outlined in red. The red basically shows you without significant technology improvement, there is very low probability that we will reach a price advantage for sodium-ion battery, taking today's technology and simply use the economy of scale. And the way that it would become competitive is if something happened to the pricing of lithium, something that Frank mentioned this morning as well. So let me now draw a few conclusions from this work. Number one, price competitive is possible, but this is only for the case of supply chain disruption specific to lithium-ion batteries. The R&D roadmap is critical to maintaining competitiveness. In fact, it is necessary. Based on today's technology and our predictions, we do not believe that price advantage would be reached at all. Finally, although I didn't discuss it, we also carefully look at the importance of market pool. So what if there's greater penetration to the EV market? What if there's penetration to the 2- and 3-wheeler? We find actually it is less important than R&D. So our conclusion from this work is R&D is very much needed, and we also make specific recommendations on what type of R&D would have the biggest impact on the pricing and the competitiveness of sodium-ion batteries 20 years from now. So this is the first example, and this is what we think is necessary to build better batteries faster, is to work backward from the economic scale. Now, for the second part of my talk, I'm going to now go down in scale to the cell level and talk about how we can do excellent engineering and combining that with data science to accelerate the understanding. And I will also likewise do a deep dive as well. So there are many experts working on this across the world, and this is indeed one of the major bottlenecks of battery technology, is because the lifetime is very long and the use cases are very diverse. So we are always in this iteration cycle of trying to examine the batteries as they operate in the real world, make predictions of how they would behave, then explore a large design space, whether it is in the battery management system, in the cell design, or in the material chemistry level. And this process must run many, many millions of times before we can converge on a battery that can be deployed. One of the major challenges in this area is, as highlighted this morning, is a disconnection between laboratory testing and real-world testing. So I'm going to show you some example from our work with Simona Honori to look at how dynamic cycling under real-world conditions can affect the aging of batteries, and how this also must be accounted for in the engineering of materials and cells. So in this study, we looked at the cell level and asked a simple question: how does realistic cycling conditions, mimicking that of a battery electric vehicle, would dictate the lifetime of the battery? So here we looked at 4 different types of cycling conditions across a total of 50 conditions, ranging from the vanilla constant current to something that is periodic. These both are very common in the laboratory. Then we look at synthetic drive cycles and also real driving cycles from data that we have captured from vehicles on the road. And to save you the details and to show you the conclusion, what we found is the lifetime depends strongly on the dynamic cycling conditions. So in each one of these plots, I'm showing a similar depth of discharge and the same C rate. The dashed line shows you the baseline case of constant current cycling, so what we would say normally do, at least in the academic setting. And the histogram shows you the broadening of the lifetime. So in fact, we see in some cases the lifetime under real driving conditions can be 40% longer than under constant current conditions. And this is more amplified at lower rates, which also point to the importance of calendar aging as well. Real cycling is difficult to understand because the design space is very complex. We're inputting real driving cycles. So here is where machine learning can come to the rescue. So we perform interpretable machine learning and look at the correlation between these dynamic, real-world cycling conditions and their relationship to cycle life. So here in this analysis, we're finding out the most crucial contributors. And the short answer is not a single factor dominates. It's a combination of factors. What these plots are showing on the y-axis are various stressors, and they describe the various aspects of dynamic cycling. And the x-axis for the plot on the left shows you basically the performance of the battery at different state of health, and the plot on the right shows you electro-specific lithium inventories across the battery as well. And you can see where the spots are darker, those are stronger influencers on the degradation of the battery. And what I want to highlight are the following. There are three factors which are extremely important in determining the real-life degradation of these lithium-ion batteries. And I also forgot to state the chemistry. This is NCA graphite chemistry with silicon. So the peak frequency of the dynamic cycling, so basically the frequency of regenerative braking, the rest at high state of charge corresponding to calendar aging under dynamic cycling, and also the extreme current during the discharge pulses. All of them strongly affect the dynamic aging. So in the next few slides, I will show you a deep dive in how we are understanding degradation under dynamic cycling at the chemistry and the materials level. Purely looking at the data-driven level doesn't tell us why the battery is aging. So we must now look a little bit deeper. And for this deep dive, I'm going to switch to LFP and look at how dynamic cycling, specifically pulse cycling, is controlling the aging of the batteries. And here we did a very, very simple experiment. We cycled LFP cells at C/20 as our baseline, so that's in blue, that's in black. Then we added a single discharge pulse for 2 minutes, right in the middle. So that's the big dip you see there at intermediate state of charge. And we compare how the voltage curves correspond to this particular pulse. So here is the result. The black line is your baseline case without the pulse, and the orange line is with the pulse. And you can see here the overpotential is substantially reduced, so the efficiency of the battery increases tremendously after the pulse. And what is the most surprising is that this 2-minute pulse has an effect that is more than 5 hours long. So you can see as you go from the left to the right for the voltage trace, the efficiency improvement is long-lasting. So this was very puzzling to us in this fundamental measurement, so we performed additional physics-based simulation to understand how LFP is responding to this pulse cycling. And here, let me walk you through some of the details. So on the top, I have a simulation of our baseline case, and on the bottom, I have the simulation of the pulse case. So let me play the movie. You're going to see basically the oxidation, the charge state change at the particle level. So this is a many particle simulation. So you can see in the case of the baseline, as you lithiate the battery, you have what is called a particle-particle behavior where the particles charge sequentially. And I apologize, I think the movie is not playing correctly. And then in the pulse case, what happens is as soon as you apply the pulse, it activates more particles to receive the current. So this is most directly seen by doing a snapshot in time. So this is immediately after the pulse. The top is the baseline case, the bottom is with the pulse. And you can see there are a lot more actively cycling particles in the second case. So what the pulse does is it increases the homogeneity of the electrode by activating more particles to undergo phase transformation. And then secondly, the pulse also serves to bypass the phase transition entirely by having a high current. And what we find here is the battery is becoming more homogeneous with the pulse due to the activation of a greater fraction of the particles. And also, we are bypassing the phase transformation. So this can be seen in the active fraction of the electrode on the top, and also the solid solution fraction that bypasses the phase transformation. So these are the results that we gain from the modeling, and we also examine this experimentally by monitoring the state of charge at the subparticle level using microscopy. So the set of particle on the left, that's the baseline case. The set on the right is the pulse case. And it's a little bit hard to see what's going on, but if I show you a histogram, this is looking at the distribution of the state of charge at the particle level. So you can see in the baseline case, most of the particles are either charged or discharged, but very few are actively cycled in the middle. But as soon as you apply the pulse, then you find many, many more particles being active in the middle. So although the average state of charge is the same, the heterogeneity is much reduced through the pulsing. So this, I think, is a good example of how we are able to understand the pulse-induced aging at the cell level and also deepen the understanding at the chemistry and materials level by performing modeling and also characterization at the single particle level. So now let me come to my final point at the materials level. So I've shown you that if we work backward from economics, we can better inform our R&D strategy. I've shown you that by embracing real-world cycling, we can make better decisions on what optimal optimization to carry out. For the final example, which is going to be very quick, is now to point out one specific thing that we can embrace as a community, which is to really think about the connection between reliability and materials mechanics. This is an area that has received some attention in the past, but I think this is a huge opportunity for us to consider, especially at the material development stage. And to make this point, I will also do a deep dive on how we're using computer vision to understand mechanics at the nanoscale, again, for lithium iron phosphate. So to understand mechanics, there are really two things we need to measure: strain and stress. When I know that at the nanoscale, then I know mechanics. However, it is extremely difficult to measure both quantities, if not impossible. And there's the additional complication in battery materials. Everything depends on the state of charge, including mechanics. So to address this challenge, we turn to computer vision and machine learning to develop a full mechanical picture of lithium iron phosphate. So let me walk through what we did. We started by measuring the state of charge of the particles at the nanoscale and also the strain at the nanoscale. And this is done by using two different microscopy methods on the same battery materials and correlate them using computer vision. We assembled this very high dimensional data set that tells us the state of charge, the strain along all directions. And then from this, we use a machine learning model guided by mechanics and equilibrium considerations to derive the relationship between composition, so the state of charge, the strain, and the stress in the system. So again, I don't have time to get into all the details. Again, you can take a look at our published work, but let me show you what we found. We're able to measure these beautiful images by combining the electron microscopy and X-ray microscopy to show how strain is distributed at the nanoscale. These are lithium iron phosphate cathodes showing the nice phase boundaries at 50% state of charge. The image on the left is the compositional map, so this is the state of charge. And then the images on the right shows you the strain distribution in different directions. Using this model, we're able to separate all the contributions. First, we isolate the contribution that depends on state of charge. So in all cathodes, lithium iron phosphate is no exception. We have a lattice constant or strain that depends on the state of charge. So the model is able to separate that out. And we're also able to separate out the elastic contribution because there is a different lattice constant between the two phases of lithium iron phosphate, and that creates stress within the system. So we evaluate this elastic stress separately from that, depending on just the state of charge. These two contributions are what's called the compositional strain, and then also the elastic strain. But because in lithium iron phosphate, as you cycle the battery, these phase boundaries must also move, and they will leave behind other forms of strain in the system, and that is the remaining one. By removing these two contributions, we're then left with what's called the residual strain in the system. And here is the strain that is due to dislocation generations as the battery cycles. So by using computer vision in this case, we're able to take a very standard material, lithium iron phosphate, and answer one of the more fundamental questions: how does mechanics accompany the cycling of these batteries as it undergoes phase transition? And this is a fundamental piece toward engineering more reliable battery material, such as lithium iron phosphate. There are many more examples to show across all three scales, but I want to come back to my main common thread. And I'll just repeat it one more time. So how do we build a better battery faster? In our opinion, we really need to put together these enormous data sets, these engineering models, these multi-physics models, and use data-driven approaches such as machine learning to gain understanding. I gave you 3 examples today. An economics example, we harvested a huge amount of data from industry, mining, minerals, and everything between. Cell data, looking at aging, and looking at nanoscale materials data. Although the 3 examples are very different, I hope you see the common thread of using the same approach toward connecting the dots. And by connecting all of these skills together, we have a better integration to understand how we optimize a more reliable battery, how we can optimize a more economical battery with the connection from the atoms all the way to deployment scale for the entire planet. So with that, I would like to thank the organizers once again for the opportunity to speak. And I just want to briefly highlight all the great people that did the work. This is really a decade worth of work with many collaborators, students, postdocs, and staff. And I'd also like to thank industry and the US government for funding this work. Thank you.
Thank you very much, Will, for this lovely introduction in how you are addressing and also tackling research challenges. Thank you so much, and I hope that we still have some time for questions. So the party will not start earlier, even if we end earlier, so please feel free to ask questions.
So I'm the bad guy. I'm in between the party.
No, actually, I'm the bad guy. I'm the bad guy in between you and the party. So, Dominik, please.
Thank you very much. So I'm Dominik Weins from the Helmholtz Institute Münster. Thank you very much, William, for your very interesting talk. You showed in your second part of your talk that there is, you see quite a difference when showing the lab scale constant current cycling and the real life data in terms of cycling performance and lifetime. What would your recommendation be for the rest of the scientific community when testing new materials so that they mimic the real life as good as possible?
Yeah, I think this is already being done by many of our colleagues in the area, which is to embrace increasingly more realistic cycling conditions. And what we found in this work is that certain materials and chemistry do not behave well under static, constant current, constant voltage conditions, but perform extremely well under dynamic conditions. So this means that there's a bit of disconnect between real-world aging versus laboratory aging, and this is something that's already mentioned. But my recommendation, which again is something that the field is already beginning to embrace, is to look at doing these experiments in the lab as early as possible, because we are making early-stage down selections in terms of materials and chemistry, typically based on constant current, constant voltage cycling data.
Thank you very much.
In the back, please.
Yeah, first, thanks for this informative presentation. I'm a third year PhD student doing the battery health diagnosis and prognosis. I think I I think one problem is quite relevant to what you just described is the multiple different scale for the resolution, the data you collected. So I do think that this is kind of causing problems when you integrate different problems in the different time scales. From my experience, like field data, normally they have very low resolution, maybe not even in seconds, maybe in minutes or in hours. What do you think? What kind of tools you can mitigate these problems by actually solving it and integrating all the scales?
This is a great point, and I would maybe make one provocative comment that I think the time scale is not the problem, it's the length scale. Ideally, what we want to learn is the aging mode of these materials in a real battery operating under real conditions, and you want to go from nanometers all the way to many centimeters all in once, and this is presently not possible. So I think, therefore, there's a big opportunity to really increase the throughput of our characterization method, our destructive and non-destructive methods, to really make sure that we can capture multi-fidelity data that is as massive as our cell aging data. Today, the cell aging data is the largest because among all the things that we can do, it is one of the easier ones. But if we can make sure that our X-ray data, our ultrasonic data all catches up in terms of the amount of data, then we have the possibility of really integrating. What I have shown you today are somewhat disconnected still, but we would love for new methodologies to come online so that we can really perform multi-fidelity measurements on real cells under real conditions.
Thanks.
Thank you. Dirk Uwe, please.
Yeah, thank you very much for your great insight in your research work. Nevertheless, I have one doubt about this long-term prediction of prices. Yeah? So when I remember back in 2012, I think we were sitting together in Germany, Europe, and otherwise, and people looked into cost developments, and I think it was predicted to have prices on cell level in 2015, so 3 years ahead of $300 or euros, and in 2020 of 200, and in fact, in 2015 it was at 200, and in 2020 at 100. So the 3 years ahead prediction was by a factor of 2 wrong. Yeah? And there were a lot of clever people in this room. My question is it possible with your model to go back somehow to the knowledge we had in 2012 and try to make the predictions and to see if we would be on the trajectory you're now predicting for the future? Because I'm still trying to understand why we could have been so wrong. And by the way, the predictions for photovoltaic cost reduction have been in the same way wrong. Yeah? And I still do not understand why all these great minds were not able to make predictions 3 to 5 years ahead. So therefore, is it an option with your model to try to bring us back to 2012 and make predictions for 2024?
Yes, in fact, we have tried this. The main challenge is that the mineral pricing, the historical mineral pricing, already baked in some of the history in the numbers that are part of our model. So we're not able to independently and ignore all of the modern day data. But Dirk Uwe, I would say I completely agree with you. Most likely, we are underestimating the cost learning. And this is why we pose the problem not as the absolute price, but as the relative price between lithium-ion and sodium-ion. So there we are a bit more confident because we're applying the same methodology to both. But I think chances are lithium-ion price decrease will come even faster than we predict. But now our numbers are on the record, so you can come back and ask me 5 years from now to see how wrong we are. But I hope we are wrong because that means we are making progress faster than expected.
Thank you.
Yes, I think I have also one more comment on this price and cost thing. First of all, costs and prices are somehow different. Okay, this is a cost model, right? It's not.
This is a price model.
It's a price model.
So it includes a nominal margin.
Okay, but at the end, prices are made by people, right? And also by, let's say, circumstances, conditions, which are, for example, subsidies, monopolies. So I think it's very difficult to really rule out this if this is basically not a scientific effect. So if a certain government of a certain influential region with a lot of raw materials decides from one day to the other that the sodium price increases by a factor of 1,000, then maybe we have a problem, right, with this model.
Yeah, so actually, Martin, this is an excellent point. We also evaluate the various policy drivers in the case of subsidy, so that can really make a big difference. But typically, we find the amount of subsidy required is enormous, more than the government can provide. Secondly, on the supply side, we also model different aggressiveness and also supply chain disruptions. So if you look at lithium, we consider 3 different cost trends going forward, and that will have different effect. So these are the various supply chain scenarios we're considering. I think the challenge for these models is we don't know which scenario will be true. All we can do is to tabulate the scenarios and take a look at the effect. But the point I want to drive home today is now that we know what scenarios could work better, then we should work towards working with our governments, leaders, working with our researchers and companies to try to make those particular scenarios, which are attractive, a reality.
Maybe one philosophical question at the end, so I'm not sure whether it's smart or not, but I just dare to do it. So you get the impression from the examples 1 to 3 that you have brought to us. So at the end, if you bring together many scientists from different disciplines, if you're using matrix concepts, if you are looking at filling the gaps, that you have basically a comprehensive approach to the problem, then basically you cannot go wrong. Okay, that is something which you can extract from as a gist from what you have said. But at the end, I think in science there are also these coincidences, right? And these eureka moments. Somebody has an idea which came up without AI, actually HI, human intelligence, right? So what do you think? Can we rule out all this in the future by this, or will there still be these eureka moments also in the future? I know it's maybe a rhetorical question, but at the end, if you are, saying, okay, I have the best way to do science and to really come to the best conclusion, I'm not sure whether that's the only approach.
I completely agree with you that the only way to make things work well is to have elements of discoveries and serendipity, to be rooted in the fundamental science. Things like AI are nothing but tools that we can use to complement those. So I hope I conveyed today clearly that we need to integrate multiple disciplines, that we need to take just beyond, not just only a big data approach, it's just one of the many elements that we require. And I would say if you look back for the past 20 years, many of the major discoveries were serendipitous. It was not engineered in any way. So I certainly look forward to making a few more discoveries in the near future.
Thank you. So at the end, if somebody has a crazy idea, don't use AI, just do it. Okay, that is basically what I wanted to say. So thank you very much, Will, for this. Next year we invite you for a talk on fast charge, and the talk will be entitled Building Faster Batteries Better, right?
Thank you.
We're looking forward to that. Thank you, Will. Yeah, as promised, a few words at the end for what is waiting for you next. The start of the evening program at the Jofel, and I said this several times when we had this meeting, Jofel is actually Münster dialect, which is called Masemat and means something like nice, beautiful, awesome. So that's the name of this club or disco or whatever you want to call it. The Jofel is actually when you go outside the building, the main exit. Then you go to the left until you are basically at the street, and then you go to the left again until this street makes an intersection with the big street. And right at the corner is the Jofel, so it's basically a 1-minute walk from here. And we are starting with 7 p.m. with the start of the evening reception and the catering, and there will be drinks. And for the sake of that, the program afterwards will be not, let's say, resulting into a noisy chaos. I would like to ask you to, when we are running the program, maybe to go a little bit down with your voices because it's very loud in this music hall. Because then we will have a lecture about the world record attempt in the formula. Student by Matthias Rohrer from Zurich. And afterwards, we will have the poster award ceremony. And this year, I can tell you, we have 4 awards because we could not really find a conclusion about 1 award. So we thought, okay, let's give 4 awards instead of 3. And also I want to mention, if the awardee or a replacement is not at the reception, then I take it, okay? I need it anyway. I never received a poster award in my life. Okay, and then at 9 o'clock there is a dance floor, and then, you know, of course you can enjoy yourself. But enjoy yourself responsibly, because tomorrow at 8:45, under the prominent chairmanship of Dirk-Uwe Sauer, we are running our 2nd day, and we are starting with the keynotes. We have 4 great keynote speakers again, addressing science policies and programs in Japan, talking about 20 years of process development, particularly recycling. Bernd Friedrich from Aachen, he is a great speaker, I can tell you. Then Rosa Palacin will give us some idea about what can we do except for lithium. And finally, we will see one of the big 3 cell makers in Europe, Northvolt. And we start tomorrow morning with Kohei Uozaki from the Japanese JST. So it's really a very good program, and I encourage you to be there, because you can have drinks every day, but you cannot hear these 4 speakers every day. So with this, I wish you all a very nice evening. Prepare yourself well, because we are starting at 7 with the program in the Jofel. Thank you very much.